All right, hello everybody to Georgia Tech Graph Theory Seminar. Our speaker today is our very own James Anderson, who will tell us about coloring graphs with forbidden bipartite subgraphs.
Thank you. And this is joint work with Anton Bernstein and Abhishek Dalwar. So in 1999, Alon, Krivelevich, and Sudakov conjectured that for any graph H, we have this constant C that depends on H, such that if G is an H-free graph of maximum degree delta, then the chromatic number of G is at most this constant times delta over log delta. So the best known result was given by Johansson in 1996. This was actually never published, but Molloy and Reed gave his proof in 2002. And they showed that if G is H-free, then the chromatic number is the constant times delta log delta over log delta. So there's this extra log delta term. Now for specific H, the conjecture has been shown to be true. So in 1995, Kim showed that as long as we forbid H, where H has girth 3 or 4, then we get this bound, that the chromatic number of G is at most 1 plus little o of 1 delta over log delta. In 1996, again in this unpublished manuscript, Johansson showed that chromatic number of G is at most C delta over log delta for some C when G is triangle free. In 1999, in the same paper from the conjecture, it was shown that if G is K1 TT free, then we can get a constant that depends on T. So the big O of T, delta over log delta. In 2014, Petty and Su improved Johansson's result from C to a constant 4 plus little o of 1 for G triangle free. And so now notice that the constant no longer depends on H. And then in 2019, Molloy finally showed that we can get 1 plus little o of 1 delta over log delta for G triangle free. And then in 2020, this O of T was improved to T plus little o of 1 for G K1 TT free. And they gave, in the same paper, they gave a lot more results for different specific structures. And so notice that this constant really depends on the graph H. It depends on T. How does this upper bound compare to the best known lower bound? Well, a construction in 1978 by Bolobash shows that there exists G with arbitrary high girth, but the chromatic number is at least 1/2 delta over log delta. So the best upper bound that we have on some of these graphs is 1 plus little o of 1, which is about a factor of 2 away from the best known lower bound. So our result, we were able to improve this T down to a 1 plus little o of 1 in the case where G is B free, where B is bipartite. And the best known bound before on bipartite graphs was a corollary of this result in 2020 by Davies, Kang, Thoreau, and Serini, where they had this constant depending on T. But we actually get something stronger. We don't just get the chromatic number has this bound, but we get that the result holds for the dp chromatic number. And if you're not familiar with the dp chromatic number, we're going to talk about it. And it's a generalization of list coloring. So all these results here actually all hold for list coloring as well. But we're going to show that the result we have also holds for dp coloring. So what exactly is DP coloring? It was introduced in 2015 by Dvořák and Postle. And we start with the definition of a correspondence cover, or DP cover. So when we have a graph G, we take a pair L and H, where H is a graph, and L is a function that sends a vertex of G to a subset of the vertices of H that has these certain properties. Each set L of V, and we usually call this the list of V or the colors of V. These form a partition of the vertices of H. Each list is an independent set in H. And for each edge in G, or for each U and V in G, the induced subgraph between their lists in H is a matching, and it's empty if U of V was not an edge in G. So as an example of this, we have G here as a 4-cycle. Each vertex becomes blown up to have 2 vertices of H as its list. And you can see that the lists, which are represented in these ovals, they partition the vertices of H, and each set in one of these ovals is an independent set in H. And then between these independent sets, we get matchings. So each edge in G is replaced by a matching, and these other edges, these other matchings are empty where they correspond to no edge in G. And so a coloring, an H coloring of G, it's a function which assigns each vertex of G to a vertex in H such that the vertex it's assigned to was in its own list. It's proper if phi of U, phi of V is not an edge in H for each U, V, and G. So back to the picture, we can think of a coloring here as an independent set of H that chooses a vertex in each of these lists. So let's see. Oh, yes, and the DP chromatic number, it's the smallest L, such that whenever H is a DP cover where these list sizes are at least L, then G has a proper H coloring. And so let's see an example of this, and particularly, as I said earlier, a DP coloring is a generalization of list coloring, and so let's see how these two cases compare. Okay, so we start with G over on the left. We have a triangle. And let's suppose these were different colors or lists we were allowing for G. Well, each of these colors gets represented as a vertex over in H, and each of the ovals represent the lists associated to each vertex in G. And so now in the list coloring case, we're going to put an edge between any 2 colors that are the same. And so now a list coloring is simply an independent set where each partition has a vertex in this independent set. So for example, in the first set, okay, we could take red, and then in the second set, well, we can't take red because it's already conflicting with the red. So we could take blue, and then in the set over here, we could take purple or green. So now this is for a list case, but in the general DP setting, we don't have to have that each color matches with its other color. We could have arbitrary matchings. So for example, here, red corresponds to green. And here, blue corresponds to green. And here, blue corresponds to purple. And hence the name correspondence coloring. And so now a proper H coloring for this cover H, well, we have to find an independent set. So for example, we could pick, again, red up here, and then blue down here. But if we did that, well, we could still pick red over here because red is not conflicting with this red over here. And so even though in G we shared an edge between these two vertices, we could still color them red. Maybe this is a good time to ask if there are any questions or if the setup is clear, what these DP covers are. Actually, I can't see the chat, so.
Oh, that's all right. I'm looking at the chat.
Okay, great. All right, well, if there's no questions, then we'll move on. So there's been some work on these DP colorings. And what's neat about DP colorings is we can ask about restrictions on the cover H instead of on G. So in those other results we were talking about the chromatic number in terms of the degree on G, but now we can do so on H, for example. So Canby and Kang in 2020 showed that when G is bipartite with a DP cover H, such that the maximum degree of H is D, and the list sizes are all 1 plus little o of 1 D over log D, then G is H colorable. In 2020, Alon and Asadi, they showed a similar result. They didn't do it in the DP case. They did it in the list coloring case, but they showed an analogous result. If you have a cover that corresponds to a list coloring, when G is triangle free, they got the same result except with an 8 instead of a 1 here. Now, in this same paper by Canby and Kang, they conjectured that when G is triangle free with the DP cover H, you can improve this 8. You improve this 8 down to 1. And so we can even look at cases where the structural limitations are completely on H and have nothing to do with G. So for example, what we show is that, well, we're not going to have restrictions on G here. What we show is we have this constant alpha greater than 0, such that for any epsilon greater than 0, there's a D naught, such that the following holds. Okay, so for D large enough and S small enough in terms of D and T small enough in terms of D, if G is a graph and H is a DP cover of G such that H is KST free, the max degree of H is D, and the list sizes are all 1 plus epsilon D over log D, then G has a proper H color. And so notice here, we're not using that G is triangle free or that G is KST free. We really only have restrictions on this cover H. And so this, however, when we do look at G and we have G as KST free of max degree delta, this immediately gives that the DP chromatic number of G is at most 1 plus little of 1 delta over log delta. And this is because if G is KST free, then its cover will have to be KST free as well. And if G has max degree delta, then its cover will have to have max degree delta as well. And so now, since every bipartite graph B is contained in a KST for some S and T, we have that the result holds for B-free graphs. You can always take this D naught to be large enough so that the result will hold. Okay, so how do we actually prove this theorem? What we're going to need is an iterative procedure known as the wasteful coloring procedure, described by Kim in 1995. And so we've adapted it here to be in the notation of DP coloring. And so essentially what this procedure does is you input a graph and it will give you a partial coloring. So this is how it works. We start with a graph in this DP cover H. And the first thing we do is we activate the vertices in V of G independently with some probability eta. So we just flip a coin for each vertex. We say, okay, you're going to be activated or you're not going to be activated. And we'll call the activated vertices A. So each activated vertex is going to get a color from its list. We'll say color of V. And we just pick a color from its list uniformly at random. And these colors, remember, we can think of these colors in the list as vertices of H. And so the set of vertices in H that correspond to assigned colors, we're going to call color of A, and these are just the set of assigned colors. So now what we do is we say, okay, for each color in a list, we'll keep that color if none of its neighbors in H correspond to these assigned colors. And we let K of V be the set of these kept colors. And the other colors, if they have a neighbor that corresponds to an assigned color, we'll just throw it away. And this is where we get the term wasteful, because we're throwing away a lot of colors. And so now what we do is, after we've gotten rid of colors, if a color of V that it was assigned was kept in its list, then we're going to set our partial coloring phi of V to be that color. For other vertices, if its assigned color was removed, then we just keep it blank. And we call these uncolored. So now what we do is we update our graphs. We take G prime to be the set of uncolored vertices in G, L prime of V to be their remaining colors or their kept colors, and H prime to be the vertices in H that corresponded to kept vertices. Okay, so I'm going to give an example of this wasteful coloring procedure so we can see how these steps actually work with a picture. So let's imagine on the left we have this graph G, and it has these lists of colors, and we can build, suppose H with some cover built as follows, right? We take each vertex of G and replace it with its list, and then we have these arbitrary matchings. So the first thing we do is we assign, or we activate colors of G. So suppose that these vertices down here in red get activated. And then for each activated vertex, we're going to pick a color to assign the vertex. And so you can see, okay, this vertex gets going to be randomly assigned green, this one light blue, and this one dark blue. Now over in H, that corresponds to these vertices. And now we're going to remove the vertices in H, which have an edge to one of these assigned colors. So here's our edges, and these vertices incident to these edges will end up being removed. So we remove all of these. And now we look at our vertex in G, and its assigned color was removed. For this vertex, its assigned color was removed. But for this last vertex, its assigned color was kept. It didn't have any conflicts. And so this vertex of G will end up getting this dark blue color. And now we update G and H. We forget about this assigned color blue. And we're left with this, the uncolored vertices of G and their corresponding lists in H. And so now notice, we started with 3 colors in every list of G. And at the end, we're left with an average of less than 2 colors. So that's why this is called the wasteful coloring procedure. However, you can also see over in H, we have much less edges, many less edges than we had before. And so in some sense, yes, we got rid of colors, but we've also gotten rid of a lot of conflicts between the colors. And so this should ideally help us to finish coloring this graph G. Oh, yes, in this case, G prime. Okay, so any questions on how this wasteful coloring procedure works? All right. So the way we prove our theorem, first, by a small modification, which I'm not going to go into the details, but we'll be allowed to assume that our cover is deregular, and this will help significantly with our analysis and our calculations. So we're going to apply the wasteful coloring procedure iteratively. And the idea is, hopefully with each round of this procedure, the size of the list, or the number of colors available, compared to the degree of each color in our graph H, we want the ratio of the degree over the list size to decrease. So if we let L be a lower bound for the list sizes and D be an upper bound for the degree in H, this ratio D over L is going to decrease with each round of the wasteful coloring procedure. When we hit the point where L is greater than 8D, we'll be able to use the Lovász local lemma to finish the coloring. And this follows from a well-known result for list coloring. We've just renamed it, the notation, to be in terms of DP coloring. So when the list sizes are at least ceiling of 2e to the delta h, then G has a proper H color. So to conclude the proof, we're going to need to show that this ratio D over L decreases, and this is the main bulk of the work. And so in order to do this, it'll be helpful to define these parameters. And the intuition behind these parameters will become clear in a second, what they're going to be. But this L prime and this D prime, we're going to show, ideally, this is the lower bound on the list size, and this D prime is a upper bound on the degree for our graphs G prime, H prime. Yeah, and we show this with positive probability that this L prime and this D prime will be lower and upper bounds for the list size and the degree, respectively. And so the ratio D over L is going to shrink by a factor of approximately this uncolored parameter, because you can think, okay, we have D over L, but then after our iteration, we get D prime over L prime. And if we ignore these error terms over here, then we see that this keep and this keep cancel out, and we're just left with approximately a factor of uncolored D times L, or D over L. So we're shrinking by this factor of uncolored, which is less than 1. We have 1 minus eta times keep, and keep is something less than 1. Now the trick is going to be showing that L prime and D prime are indeed lower and upper bounds for our list size and our degree. And so the way we do that is we're going to show that L prime of V, the size of L prime of V and the size of the degree of H prime, max degree of H prime, are highly concentrated around their expected values. And so now the intuition behind these parameters, I'll explain. This keep is exactly the probability that a vertex in H is kept, and uncolor is the probability that a vertex is approximately the probability that a vertex remains uncolored. And so the expected value of our list size in L prime is going to be keep times L. Now it's too much to hope for that the list size of all our vertices is going to be greater or equal to its expected value. So we need to add a little error term. And so now this L prime becomes a lower bound. If our list sizes are highly concentrated, they'll be near this keep L term, and in fact, they'll be within this error bound. And then the same for D prime. It turns out that keep times uncolor times D is going to be the expected value for the degree. of a vertex in H. And again, we have to have a small error term because it's too much to hope for that the degrees are all going to be less than their expected value. And so as long as we can show that this, the size of L prime of V and the size of the max, I guess we don't need the size here, just the max degree of H prime. As long as we can show that these are highly concentrated, we'll be able to have that this ratio is shrinking until we can apply the LLL result. Okay, so we're going to let little l prime of V be the size of the list and d prime of C. Technically, we need to define it this way because we don't want to define it as the degree of a vertex in H prime. If just in case our vertex ends up not being in H prime, we still need it to be well defined. So if our vertex is in H prime, you can think of this as the degree of that vertex in H prime, but it's a small technicality. So we'll show that the following results hold. First, that the expected value of L prime of V is keep L, like I said before, and that it's highly concentrated around its expected value within that error term we saw before. And then again for our d prime of C, the color degree. Its expected value is at most keep uncolored D with a small error term, and the probability that it's exceeding its expected value by this error term is quite small. Now, the first three of these statements follow really similarly to Kim's proof in 1995, just adapted for DP coloring instead of list coloring. But it's this last statement where we have to use a different approach. And particularly because Kim's proof used girth 5, and now we're not going to be assuming girth 5, we're just going to be assuming that the cover is KST free. And so we need to somehow do something different for this case. So the rest of the talk, we're going to focus on concentrating this d prime of C. And actually, it's going to be easier to focus on the concentration of these two other sets. And so I'll explain formally what these sets are, but then I'll explain the intuition. Okay, so U, we're going to be looking at, we look at C and we look at all of its neighbors in H. And we look at the neighbors, the C prime, whose underlying vertex is blank. And we want to essentially count those. And then K here, well, it's going to be those neighbors, and those neighbors that end up having no conflicts, except perhaps the chance that C actually ends up being the assigned color of V. And then the reason we need this technicality is, well, if V ends up being assigned C, then none of C's neighbors get kept. And so this neighborhood here actually drops, it becomes empty. And we don't get that this K is highly concentrated, the size of K. We need this small technicality here. So what's the intuition behind these? Well, U can be thought of as these vertices whose underlying vertices are uncolored. So U for uncolored. And K can be thought of as the colors in the neighborhood of C that end up being kept in their list. Of course, unless V is colored C, but that's a small technicality. And if we, I should have said, if we concentrate U and we concentrate K, their intersection is really closely related to this d prime of C. And so if we can concentrate both of them, we'll be able to concentrate their intersection and with some, adding in some error terms, but eventually we'll be able to concentrate d prime of C. So we'll focus on how we concentrate U, and then we'll focus on how we concentrate the size of K. And now concentrating the size of U, the usual approach is to use Talagrand inequality. So I'll state what Talagrand's inequality says. If we have a non-negative random variable, which is a function of n independent trials, and for us, these trials are going to be the color assignments of vertices. So if we have for some C and R greater than 0, if we have changing one of these trials can only affect X by some amount C. And if for any S, if X is at least S, then we can find a set of at most RS of these trials that will ensure X is at least S. Then we get some nice concentration results. We have essentially that X is well concentrated. However, this isn't going to work for us. And what is the reason why? Well, the reason why is if we change the color of U for some U vertex of G, so we're thinking of some color in our graph H, and if we change the assignment of U to some other color in our graph H, we could affect U by quite a large amount. In fact, we look at all the colors that this assigned color in H sees, which are activated. And it turns out, okay, changing this color, well, now we could change it so it conflicts with many more activated colors, and that will affect the size of U. So one small change can affect the size of U by quite a bit, and this is why we can't use Talagrand inequality. However, remember, at the beginning of our wasteful coloring procedure, we activated a number of vertices, and the proportion of vertices that get activated is actually really small. And so it's with a relatively low probability that a vertex color of U in H is going to see more than approximately the square root of log D neighbors, which correspond to activated vertices. So it's with a pretty low probability that a change in one of these colors, the change in the color assigned to U, will actually affect a large number of vertices contributing to the size of U. Because remember, what is the size of U? The size of U is essentially counting these vertices that end up being uncolored. These vertices in the neighborhood of B that end up being uncolored. And so in order to do that, the vertex, the color that this vertex is assigned has to see a conflicting neighbor in H. And so it's all about the activated vertices. And since there's few of them, well, the outcomes where the color of U sees more than approximately the square root log D activated vertices, this is going to happen with very small probability. So small, in fact, that we're going to say that this is an exceptional case. And if we had a version of Talagrand's inequality that could deal with these exceptional outcomes, we would be in good shape. And in fact, we do. In 2015, Brun and Hos showed that for X non-negative, the function of n independent trials, if we have omega be the set of outcomes, if we have omega star, the subset, which is going to be these exceptional outcomes, we're going to show we can do the following. So if we have C and S here, greater than 0, or greater than 1, greater than 0. And now the certificates are going to be a little more tricky, but if for all Q greater than 0 and non-exceptional outcomes, we can show that there's a set of at most S trials, so that changing the outcomes of at most Q over C of these trials to some other non-exceptional outcome can decrease X by at most Q. If this holds, and if the probability of an exceptional outcome is quite small, then we get our nice concentration result. And so what exactly is this saying? I mean, this is a lot to take in, but essentially it's saying, okay, as long as we can find this set of S trials so that changing those trials by a small amount doesn't decrease X by too much, then we'll get our nice concentration result. As long as we can throw away and ignore these exceptional trials. And so using this, we end up, or we're able to concentrate the size of U. Okay, so now we have to focus on concentrating K. And remember, the size of K was the number of vertices that are kept for this vertex V, the number of colors that are kept in its list. So again, the usual approach is to use Talagrand's inequality, but once again, this won't work. And why? Well, it's possible that a change to the assignment of U can affect K by the amount of neighbors that it sees in the neighborhood of C. And as opposed to the case with concentrating U, now we can imagine, okay, if you change the color assignment of a vertex U, so we change it from one vertex in H to another vertex, well, now it's going to affect everything it has an edge to in the neighborhood H of C. And it's going to remove all those colors. And so we could, in theory, changing this color assignment of U could affect the kept status of all these colors in the neighborhood of C. And this is too large of a change to use Talagrand's inequality. Now, this is sort of the same problem that we had with concentrating U, but we were able to get over this problem with U because of the activation. The number of activated vertices was so small. But here, colors are kept or not kept regardless of the color assignment of the underlying vertex. And so a change to the color assignment of U can still affect many colors in the neighborhood of C. So even exceptional Talagrand inequality won't work here, and we'll still need to do something different. What we really need to do is minimize the impact on vertices which can affect K by too much. And it's here that we're going to use KST freeness. So in our diagram, we can think of C. We think of the neighborhood of C and H in its second neighborhood. Now, we're not assuming triangle freeness. And so really, this neighborhood and the second neighborhood could intersect. But for the sake of the simple picture, I drew them as disjoint. But in reality, you could have a vertex that's in both the neighborhood and second neighborhood. And so the idea is, okay, a vertex here, you can see it's affecting a lot. It has edges to a lot of neighbors of C, as opposed to this vertex here only has one. So if we, for example, had our color of U first being this color, and then we switched it to be this color, well, now we're going to remove 4 colors from the neighborhood of C as opposed to 1. And so a small change can have a big effect on the size of K. So these vertices here that have a lot of edges are the ones we'd like to somehow get rid of. Which leads us to the following definition. If some vertex in the second neighborhood of C has at least d to the 1 minus delta, or some small delta, we're going to call it bad. It's going to be good otherwise. And so these are our bad vertices because they have a lot of edges. Now, if C prime in the neighborhood sees a lot of these bad neighbors, we're going to call it sad and happy otherwise. So these vertices over here in blue, they each see 2 bad neighbors, so they're sad. And these other ones, well, they only see 1, so it's relatively small, so we'll call them happy. And so what's the idea? The idea is the number of these sad vertices is going to be quite small. And why is that? Why the number of sad vertices is going to be small? Well, this is where KST comes in. We have by the Kováry-Schacht-Turan theorem in 1954 that if G is a bipartite graph, partitions of size M and N, and if it's KST free, then we have a bound on the number of edges. So this bound on the number of edges, well, that tells us there can't be too many sad vertices, because the sad vertices have edges, have a lot of bad neighbors, which means they have a lot of edges to these bad vertices, and these bad vertices had a lot of edges, and we just get way too many edges. So we can't have too many of these sad vertices, and we can essentially ignore them. We'll get a small error term, but that won't affect our concentration of K too much. And so now we've eliminated the impact of these sad vertices. And what's left over are these bad vertices that we want to eliminate the impact of. And if we've gotten rid of the sad vertices, well, a happy vertex doesn't see too many bad vertices. And so really we can ignore the impact of these bad vertices as well. And so what we really focus on is concentrating this Z tilde, which is the number of happy vertices with a good conflicting neighbor. Because now if we change a bad vertex, the coloring of a vertex U and G to a bad vertex, well, this isn't going to affect if a vertex in H was kept or not, because if it had a good conflicting neighbor, it's already getting thrown out. And so it doesn't matter now the impact of these bad vertices. And because we've gotten rid of these sad vertices, the number of happy vertices with a good conflicting neighbor is relatively close to this amount. Okay. And so there's still a problem. We still haven't gotten over our hurdles. The color of U, changing the color of U, it can still affect Z tilde by D to the 1 minus delta, which is still too much to apply Talagrand's inequality. What we really need is a factor much less than the square root of D. And because this delta is quite small, well, we don't have square root of D. We have something close to D to the 1. So to get over this, what we do now is we partition the happy vertices into sets of size approximately d to the tau for a small tau. So here's our picture. We have C, we have its neighbors. We got rid of the sad vertices. We just have our happy vertices, and we split the happy up into these sets. And so each of these boxes now, we're going to say is intersecting those with the vertices which have a good conflicting neighbor. We're going to call these Z tilde sub j. And now if we can show each of these pieces are concentrated, then we'll have the whole thing is concentrated. And now it turns out that changing the color of U can affect Zj tilde by at most D to the tau minus delta. Tau and delta are going to be close enough together that this is going to be much less than the square root of D to the tau. And so we'll be able to apply Talagrand's inequality to each individual piece to concentrate each Z tilde sub j, which will thus concentrate Z overall. And then as we said before, Z tilde was related to K, the size of K. So we'll be able to concentrate the size of K, which was the number of these kept colors. And now we have U concentrated, we have K concentrated. If we put them together in a clever way, we get that D prime of C is concentrated. And so going back to just the overall idea, now we would have that the ratio, because the size of L of V and the size of this D of C are concentrated, we have that this ratio Li or Di over Li decreases. We apply the iterations over and over again until we get to the point where we can use our local lemma result, and that gives the end of the proof. Okay, so that's the end. Are there any questions?
Yeah, let us thank James. And yeah, are there any questions?
I have a question.
Sure.
So in the future, when you move on to broader, or if you move on to broader classes of graphs than KST, do you think that the wasteful coloring will still be productive, but you'll have to change the analysis? Or do you think there's some class of graphs that we would care about where wasteful coloring won't be like productive and you'd need a new strategy?
I'm hopeful that it will still be quite productive. I think that the issues with it occur when you have a lot of dependencies, and so that's why it's been very useful to use in the Girth5 case, even in the triangle-free case. But obviously, it has its limitations because the analysis can become quite tricky, especially doing these concentration bound. But we are hopeful that we can extend this to K1TT free graphs. And we do think a version of this iterative procedure will work there.
Yeah, if I may add, it's just even for triangle-free graphs already the procedure, like Johansson's procedure, is a bit different from this and more complicated. So things kind of get more and more involved the more complicated the graphs are somehow.
So what is the extra step for triangles that you need to do?
Well, I guess the procedure is similar, but the analysis is very different because you cannot prove that the degrees are concentrated anymore in that case.
Yeah. That's most likely a proof artifact, or?
No, I mean, they actually are not concentrated. It's kind of easy to see that so the degree of an individual color might not be a concentrated random variable. So you have to do something. I mean, one thing you can do is like prove that the average of the degrees of the colors in the list is concentrated, something like this. But
that's what Alon and Asadi did in their argument when they got this 8 factor.
So can you, just out of curiosity, because I mean, historically, I'm quite interested in these concentration things when some bad things happen. So can you explain maybe again in the second? So I think the first step, that will still work in the general case, right? So what is the problem in the second case precisely? Can you maybe?
Oh, maybe I can go back. So these, for example, you mean this case?
So you said one that you use this exceptional version. For the first one, that one that didn't use anything, right? But so the second one, what is in the second case the main problem again that I?
Concentrating the size of K.
Yeah. So what is the main obstacle here again? Can you just?
Yeah. So the main obstacle here is changing the color assignment of a vertex in G to something different in H could now affect many different colors being kept. Maybe if I have a picture. Right.
So can I ask you, how does this fit in the general picture? So is it still, you're using this union bound plus this, or using local Lovász lemma plus this, or what is the general framework we're working in here?
It's the local lemma. So we show these concentrations for the so the degree and the list sizes, and then using the local lemma, we say with positive probability at each iteration we find this G prime and H prime, and then we can keep iterating. And we also ensure that even while we iterate so much, the list size doesn't get small. Like it doesn't, no list goes to 0 colors, which is where the actual being larger than D over log D is required.
Okay, so what is the main problem here? Can you just, so because you're saying you're going to the second neighborhood, or?
Yeah, so I guess the problem is a vertex in the second neighborhood, when a vertex in G, its color gets changed to something else, if it gets changed to something in this second neighborhood, it could affect a lot of colors in this first neighborhood being kept or not. And then that in turn affects the color degree of this vertex C. Because now it could see a lot more colors. I don't know if Anton or Avi, you want to elaborate on that.
Yeah, so we're, if I may say, yeah, we are trying to count how many colors that are neighbors of C that don't have or do have a conflicting neighbor, right? And in principle, now changing one of those colors in the second neighborhood can affect this quantity by a lot, by as much as the degree of that color is, right? So if you don't know anything about the graph, this could prevent concentration. This is a non-Lipschitz random variable somehow. So I want to use that we're KST free to show that there are not too many of these colors that can affect the quantity by a large amount, and somehow argue that we can still prove that the random variable is concentrated despite that they're there.
Mm-hmm.
Yeah, and the problem is this, as James was saying, there's this sort of a two-step thing, because even once you somehow did this argument with bad vertices and sad vertices and you remove them from the graph, somehow the conditions are such that still changing one of the colors can affect the random variable by quantity that is like d to some power that's close to 1. Strictly less to 1, but still close, and so you cannot apply Talagrand directly, so we need to do this additional trick with a random partitioning of the neighborhood itself, and proving that somehow, if you count the vertices in each of the parts of the partition, then those random variables are sufficiently concentrated. I don't know if this answers your question, Lutz.
I think it's right now too much for me to take in online, because I think it seems to be quite a delicate thing. But yeah, I was just asking because I have a little soft spot for these kind of arguments, so that's why I was curious.
Yeah, we can discuss this offline if you'd like. Are there any more questions meanwhile? Okay, if there are no questions, then let us thank James again.